Hello everyone, I hope you are doing alright. My name is Tiago Essa and today I will be presenting our work on LLM-based interpretable rules for electric vehicle charging tariffs. The main idea here is to use large language models to transform complex tariffs optimization models into simpler rules that are easier to understand. We know that dynamic EV charging tariffs can help reduce costs and emissions by encouraging charging at better times, for example when electricity is cheaper and when renewable generation is higher. However, the optimization models behind these tariffs are often complex and work like black boxes. This makes it difficult for users, for operators, and even for decision makers to understand why a certain tariff is chosen. To address this problem, we propose an LLM-based rule-generated framework. This slide presents the proposed approach, which can be understood as an evolutionary rule search framework. This framework starts with a long-term execution of the optimization model in order to create a data frame that is to be provided to the LLM. Then, the model proposes candidate rules to imitate the optimization. Afterwards, these rules are evaluated according to two criteria: predictive performance, which is measured by the mean absolute error, and interpretability, which is measured by the number of mental operations necessary to understand the rule. Then, following an evolutionary perspective, another LLM acts as a mutation operator. Basically, it suggests changes to improve the current rules and generate new candidate solutions. For promising rules, numerical optimization is applied to tune the numerical literals while keeping the rule structure unchanged. Finally, Pareto selection keeps the best trade-offs between predictive performance and simplicity. Results show that the LLM evolved rules reach comparable errors to those of classical baselines, such as linear regression and shallow decision trees. However, the key point here is the evolutionary trend. On the left, each curve represents the evolution of the best candidate across different routes. We can see that the search naturally moves towards the bottom left corner, where the mean absolute error is lower and the number of mental operations is also lower. This means that the mutation, the numerical tuning, and Pareto selection are progressively improving the rules, not only in terms of imitation, but also in terms of interpretability. On the right, we show an example of the final output, an explicit if-else logic instead of a black box prediction that combines load, renewables, market prices, elasticity, and hour as features. In conclusion, large language models can help translate EV tariff optimization into interpretable rules, being competitive with machine learning baselines. Therefore, this framework can increase trust and adoption of dynamic pricing for EV charging. Future work will focus on reducing computational costs and improving the determinism of the generated rules. Thank you for listening to my presentation. Feel free to contact me through my email if you have any recommendations or questions. Thank you.